Hi, so we're moving on to 15.4, which is talking about heterogeneous equilibria. So heterogeneous means something very similar to what it meant when we were talking about catalysts. It's talking about the state of matter. So heterogeneous equilibria is when one of the components in the equilibrium equation is not a gas or aqueous. So that means solid or liquid. When you have solid or liquids in the equilibrium, we get to leave them out of the equilibrium constant expression. If you look at this reaction here, this is the decomposition of calcium carbonate into calcium oxide and carbon dioxide. And you notice that two of these are solids. We get to leave them out of the equilibrium expression. And that's basically because they're not going to change in their concentration. Since solids and liquids have a constant composition, meaning that like their concentration is basically their density, and density and concentration are maybe a little bit dependent on temperature, but honestly not much. They're sort of considered constant throughout it, and so we don't need to include them in writing the equilibrium constant expressions. So for example, in A, if I look at these, this is a gas, this is a gas, this is a gas, but that guy is a liquid. So Kc for this reaction is the concentration of carbon monoxide over the concentration of carbon dioxide times hydrogen gas. In the next one, right, I have a gas and a gas, but I can leave out these solids because their concentration isn't going to change in the reaction. Kc is equal to the concentration of CO2 squared over the concentration of CO squared. And now moving on to 15.5, calculating equilibrium constants. So far, every single time that we've had an equilibrium constant, it has been given to us. The number has been given to us. So we're going to learn a little bit about how we can calculate equilibrium constants, and then also we will move on from there to figure out when I have the equilibrium constant, what I can figure out mathematically from that. So we're just going to start right off with a practice problem here. It says a closed system initially containing 1 times 10 to the negative 3 molarity of H2 and 2 times 10 to the negative 3 molarity I2 at 448 degrees Celsius reaches equilibrium. Analysis shows that at equilibrium, the HI concentration is 1.87 times 10 to the negative 3. Calculate the equilibrium constant, the actual number. So the way that we do this is by using what we call an ICE chart. So ICE stands for initial change equilibrium. We're gonna notice that this is kind of similar to those BCA charts when we were learning stoichiometry last year in quarantine. We talked about using BCA charts in order to keep track of the amount of reactants and the amount of products. We can do the same thing for equilibrium reactions. So the starting H2 concentration is given to us as 1.000 times 10 to the negative 3, and the I2 as 2.000 times 10 to the negative 3. And because it doesn't say that there was any HI at the start, we're just assuming it's 0. Then it reaches equilibrium, and it tells us that the HI at equilibrium is 1.87 times 10 to the negative 3. So I know that this is 1.87 times 10 to the negative 3. So it tells me that right away. So now I have to figure out every other box in this problem. Well, if the HI started at 0 and now is 1.87 times 10 to the negative 3, it must have gone up by 1.87 times 10 to the negative 3. It means that the reactants must have gone down by something. And if I look at the ratio of the coefficients, it looks like the HI gets made at twice the rate of the H2 and I2 disappearing. So what that means is that the I2 will go down at half the rate. So for every HI that gets made, half the amount of I2 gets used. So I take 1.87 times 10 to negative 3, divide that by 2. And that is 9.35 times 10 to the negative 4. And remember, the HI went up by that amount. These will need to go down by that amount because in order for the reactants to make products, some of them need to react. So their concentration is going to go down. So I actually do the subtraction here. I get 6.5 times 10 to negative 5 and 0.001065. Well, now that I have that equilibrium row, I can write the equilibrium constant expression from the balanced chemical equation. And now plug in the numbers from the equilibrium row. And numerically that comes out to be 50.5. So I set up my ice chart, plug in what I know. I'll always be able to have enough information to figure out the change row, one of the values from the change row, and then I can use basically stoichiometry to figure out how the other reactants or products increase or decrease in concentration. So here's another problem. It's done in exactly the same way, but maybe try and do this one on your own. And then, so pause the video, try it on your own, and then restart the video and see how you did. It says initially the vessel is charged at 1000 Kelvin with SO3 gas at a partial pressure of 0.50 atm. So SO3 is 0.500 atm. At equilibrium, the SO3 is 0.200 atm. Calculate the value of Kp. So we would start out with none of these. I would figure out that this guy would have to go down by 0.300. And then look at the coefficients. Because SO3 and SO2 have the same coefficient, SO2 is going to go up by 0.300. The coefficient of the O2 is 1. It is half of SO3, so therefore it is going to go up by 0.150, or half that. So now Kp is equal to the partial pressure of the SO2 squared times the partial pressure of the O2 divided by the partial pressure of the SO3 squared. Plug in our numbers. We get 0.300 squared times 0.150 over 0.200 squared. And my answer is 0.338. So we'll do lots more of these. This is the first day that you're ever doing an ice chart. It's a big day because we're going to do a lot of these come next chapter especially.